Welcome back to Physics 11. So this is going to be the last video for the dynamics and application of Newton's laws sections. So this section talks about apparent weight, and this is something you might have experienced if you were ever in an elevator. So let's talk about apparent weight. So first of all, when a person is accelerating upwards or downwards, they can feel that they are heavier or lighter than they actually are. And we call this the apparent weight. So even though their actual weight, the force of gravity, m times g, is the same, their apparent weight differs. So the apparent weight itself is going to be the normal force that supports us. So that's what we actually feel. So for example, if you're just standing on the ground, you're applying a force on the ground, your m times g, but you can't feel your force that you apply. You only feel the opposite force, the normal force. So if you remember Newton's third law, for every action is equal and opposite reaction. So for example, if you apply a force of mg on the ground applies opposite and equal force, normal force on you. That's the force that you feel. So if the Fn is bigger than Fg, you're going to feel heavier. If Fn is lower than Fg, you're going to feel lighter. Or you might feel weightless if there is no normal force at all, so whenever you're in free fall. So let's take a look at some cases. Now you notice that it asks you to come up with some cases when you feel heavier than normal, you feel lighter than normal, or equal when you are in an elevator. So I might talk about it, but in this case we're talking about it, student jumping off a desk. So the first case says, what is the apparent weight while standing on the desk? Well, if the student, represented by this block here, stands on a desk, there's going to be a force of gravity, Fg, and a force opposite to that, the normal force. In this case, the acceleration is 0. Therefore, if you were to write the F net, you're going to end up with Fn, so if you make the positive up, minus Fg equal ma, and again this is 0, so we're going to end up with Fn equal to Fg. And if that's the case, you're going to feel your normal weight. So for example, in the case of apparent weight feeling the same as the your actual weight in an elevator, that would mean that, if we go back to here, that would mean that the elevator either is not moving or it's a constant speed, moving constant speed up or down. So the next case is, what if the student jumps off the desk? What is their apparent weight while in the air? So if the student is in the air, there's only one force, and that's going to be force of gravity. Fn is not present, therefore Fn is 0, so there's no apparent weight, because again, apparent weight is your normal force. So you will feel weightless. Now, what if the student jump off the desk, and the question is, what is the apparent weight when they hit the ground? So in this case, when they hit the ground, they're actually going to accelerate towards the ground. They're going to decelerate because the ground will stop them. So they will decelerate. So the acceleration of their body is actually going to be in the opposite direction of motion. So in this case, the acceleration is going to be upwards because it's going to be opposite direction of their motion. So they're going down, hit the ground, the body keeps moving towards the ground. So in this case, the normal force is going to end up being bigger than the force of gravity. So to show this, let's write our F net equation. So in this case, our normal force vector is going to be bigger than our Fg vector. So again, here we're going to have our okay. So if you solve this for the normal force, we end up with Fg plus ma. So as you can see, our Fn is not going to equal Fg. Fn will be greater than Fg because we're going to add this mass times acceleration there. That's why I end up feeling heavier. So in an elevator, you normally feel this when, for example, if you're going up from rest, so you feel like you're heavier, or maybe if you're going down and stop, then it kind of you feel like you're getting squished, so you feel heavier than normal. All right, so let's take a look at some actual examples. We can actually calculate some of these normal forces or the apparent weight. So here's, again, this can happen in an elevator just like whenever you jump. So for example, we have a 65 kilogram person in an elevator that is traveling upwards at 5 meters per second. What is their apparent weight? Now notice here that the velocity here is constant. So whenever you have constant velocity, your acceleration is going to be 0. So if acceleration is 0, then our Fnet is going to be 0, and therefore Fg is going to equal Fn. So again, your Fg is going to be the same as your Fn vector. Okay, so no acceleration means that you will have, again, Fn minus Fg equals 0, and you end up with this. So apparent weight is the same as the actual weight. Now the same person is in an elevator that accelerates upward at 4.9 meters per second squared. So now it's accelerating. So your Fnet is not going to equal 0. So what is their apparent weight? So again, here our Fn, our Fg, acceleration is upwards. So I'm going to make my positive to be up so that my Fnet equation, the ma in the Fnet is going to be positive. So I end up with Fn minus Fg equal positive m times a. Okay, so in this case, again, if you solve for Fn, you end up with Fg plus ma. So this will make you feel heavier. So if you plug in the numbers, m times g plus m times a, our mass is 65, 9.8, 4.9. You will get 960 newtons. Okay, so versus just your weight. So this is your actual weight, which is again is going to be your just Fg, which is 65 times 9.8, and this equals to 637 newtons. So you will feel heavier. So again, in this case, Rfn ends up being greater than Fg, and you will feel heavier because of that. Now the last case says the elevator reaches the top floor and decelerates at 4.9 meters per second squared. What is their apparent weight? So in this case, because it's decelerating 4.9 meters per second squared, it's positive downwards. So now I'm going to make my acceleration to be positive down. So my Fnet equation, I'm going to have Fg being positive and Fn being negative. And this is going to equal to positive ma. You could also, if you, for example, chose positive to be upward, you just need to remember to make your acceleration here negative, so your MA would be negative. So this is one way to do it. Another way would be, again, to make your MA negative. So again, if you solve for the normal force, you end up with, let's see, we get negative Fn equal to MA minus Fg, and then you can flip the signs on all of them by multiplying by -1, so end up with Fn equal to positive Fg minus Ma. And if you plug in the numbers, again, Mg minus Ma, what do we get here? 65. So 65 times 4.9. So in this case, we got 637 minus the acceleration, so we get 320 newtons. Okay, so again, versus the just the Fg equal to 640. So you feel lighter, in this case almost twice as light. So our Fn is much smaller than our Fg. So again, our net force is downwards. So we end up with normal force less than Fg. Sorry, kind of overlaps here a little bit. Okay, so let's take a look at one more case here. So here we have another person, 85 kilograms, in an elevator, and the elevator goes from the top to the bottom floor. Find their apparent weight when they accelerate downward at 3 meters per second squared, when they continue downward velocity of 12 meters per second, and then accelerate upwards at 3 meters per second squared. So let's take a look at the first case. So like I said, there's two ways you can deal with this. So for example, you moving down and the acceleration is down, what you can do is choose the acceleration to be positive downwards. So you pick your, let me pick a different color. So when you draw your free body diagram, you can choose your positive to be down, because our acceleration here is positive. So if you do this, then your net F net equation is going to equal to negative Fn positive Fg. And then positive Ma, right? So solve this for Fn to get the apparent weight, which means we're going to move the Fn to the right, Ma to the left. We end up with Fg minus Ma equal to Fn. So Fn will equal to Mg minus Ma. We can plug in the numbers. The mass is 85.0 times 9.8 minus 85.0 times 3. So in this case, we get 578. So the person feels lighter than the actual weight. Now, as I mentioned, you can do this in a slightly different way. For example, so this would be another way you could have done this. If you draw a free body diagram, and let's say you want to stick with the kind of the convention for making the positive to be upwards, you just had to read the question carefully, because here the acceleration is downwards. So if you make this positive, you got to remember that the acceleration would be negative 3.0. So that's the only difference that you have to keep in mind. Or basically make your acceleration negative, so then you can plug in positive 3, but you gotta remember there's gonna be negative you had to take care of. So in this case, if you wanted to do it this way, so let me split this, your F net equation will look a little different. Your Fn is gonna be positive. Fg is gonna be negative. So, like I said, you either plug in the negative 3 later on when you actually do the calculation, or you stick this negative here and make this your negative MA. In that case, you don't need negative there. But you have to remember about that negative. So pay attention to the question so you can set up your free body diagram according to the question, or remember you'll have to take care of the negative somewhere. So in this case, again, if you solve this for Fn, which is our apparent weight, you see that you still end up with the same equation. You end up with Fg minus Ma, just like before. So these are the same. Fn equals Fg minus Ma. And again, if you plug in the numbers, you're going to end up with the same answer. Okay? All right, so let's take a look at part B. So part B, the person continues to go downward at velocity of 12 meters per second. Now in this case, the acceleration is going to be 0. If the acceleration is 0, if you draw a free body diagram, let's make the positive to be up. So this is our normal force, Fg. So our F net is going to equal to Fn minus Fg, and our Ma is going to equal 0 here, so this is going to go to 0, which that means that our Fn will equal to Fg. So this is going to be the same as the actual weight of the person. So in this case, it's going to be 85.0 times 9.8. And this equals to 833. Okay? So Fn equals to Fg. The apparent weight is the same as the actual weight. Again, pay attention to the question. This is velocity, not acceleration. So the last case, in this case, it's accelerating upward at 3 meters per second squared. So again, you're going to pick your direction to be positive. If it's accelerating upward, I'm going to pick that my acceleration and the positive is going to be up. So my F net will equal to positive Fn minus Fg equal to positive Ma. Okay? So here again, we're solving for Fn. So we're going to end up with Fg plus the Ma. So you're going to feel heavier because you can see that Fn is going to be bigger than Fg because we're adding the Ma to it. So we're going to plug in the numbers. Let's do it in here. So we have 85 times 9.8 plus 85 times 3.0. So in this case, we get 1,090 newtons. So much heavier than the actual weight. Okay? All right, so again, the one thing you have to remember is that apparent weight talks about the normal force, and then whenever you have questions dealing with apparent weight, pay attention to the direction of the acceleration because you have to take care of the negative sign in some cases. So to summarize here, again, when objects are in free fall, there is no normal force acting on them, so we call this weightlessness. For example, astronauts, when they're in space, if you remember from the first section on universal gravitational law, these objects are in constant free fall. So we call this weightlessness. because even though they have weight, they have the m times g, but because there's no normal force, they don't feel it. Okay, so again, that's why they float in their like a space station, and the gravity seems like it's not affecting them. All right, so in order to prepare themselves for this experience, they train on a plane that's called the Vomit Comet. So the plane either goes up really fast and then comes down really fast. So then the astronauts actually have no normal force, so they're in free fall, and they can basically experience that feeling as if they were in outer space. All right, so attached to this is a quick, or not very difficult, I would say, elevator problem, which is more of a descriptive kind of assignment. You have to do a little bit of calculations, but a lot of stuff is kind of given to you already, and I've attached the key to that as well.